So yeah, let me start regarding the DNS first quickly. So as I mentioned earlier, for example, you are browsing a facebook.com. What all are the things will happen in background? The first checkpoint is DNS. As a human beings, we will be not able to remember the IP address. The 192.168.0.1 something, we were unable to remember the numbers. That is the reason why we will be able to remember only FQDNs. Hence we have a DNS who will help us to provide these address, which can be recognized by the devices. The human beings only can remember the FQDNs, and the machines can only work with IP addresses. So I want to browse a facebook.com. For that, I need an IP address to browse the facebook.com. So that IP address I'll be getting from the DNS. So once this is client, my client will send a DNS query to the local server or the ISP, Internet Service Provider cache. Because in our locality there will be many of the users who will be accessing facebook.com, so that in the cache we will be having the IP address of facebook.com, so that once I have an IP address of the facebook.com, I'll be able to get the response from the local server or local cache. So if I don't have the IP address, if I did not get an IP address from the local server or even from the ISP cache, the same DNS query again sent to the top level domain. The top level domain is nothing but .com, .org and .net. As facebook.com, this belongs to .com. So in top level domain we also have a .com related an IP address. So the same query, DNS query, will be sent to the .com top level domain. So in this .com list we will be checking for the IP addresses of facebook.com. So if I don't find the IP address of facebook.com from the top level domain, the next DNS query will be sent to the authoritative server. Authoritative server is the last check where we will be having a DNS response for sure. So we will be getting a response from the authoritative server to access the facebook.com. So once the query is sent to only local server or ISP cache, that is called as recursive query. If the DNS query is sent only to the local server and we got an answer from the local server and the ISP cache, that is called recursive query. If my local server and the ISP cache don't have the response of an IP address, then the same query will be sent to other servers, like as I mentioned, top level domain server and also authoritative server. So this process of getting an IP address, it is called as iterative query. Okay. So this is regarding DNS. So basically DNS work on port 53. So yeah, let me show here the DNS. This is the packet capture I just randomly taking, which I'm currently working on one case. So basically the DNS will work on port 53. So let us take the query. So this is the query. My device is requesting for a query to get an IP address for gateway.zscaler2.net. So let me find the response. Here we could see in the next arrow, which is nothing but the response. So let me click on this domain name system. DNS stands for domain name system or domain name server. So here we could see the queries. So here my query is for gateway.zscaler2.net. And here I got an answer. That is, I got an IP address of gateway.zscaler2.net, which is 147.161. In this way, we have to check this in the Wireshark packet captures. Wireshark is nothing but it is a tool where we will be capturing everything. Whatever the applications are running in your machine in background, everything will be captured via Wireshark tool. So we can directly check at what point, at which header exactly it is failing. Is it failing at the TCP level? Is it failing at the DNS level itself? Or else it is failing at the SSL handshake. So this is the DNS. To browse some URL, the first check is DNS. So once we have a response, we have an IP. So we have a DNS resolution successfully happen. The next check for the URL is TCP. TCP is nothing but transmission control protocol. Okay. So this transmission control protocol have a three messages. This is my client and this is my server. Client and server. So my client want to establish a communication with the server facebook.com to get or to retrieve data from the facebook.com. First I need to have a communication, then only I'll be able to get a data. In a DNS I just found the IP address of facebook.com. Now I have an IP address. So the next step is to establish a communication with the facebook.com. For that, so my device will send a SYN message. SYN is nothing but synchronized message to the server. This synchronized message is nothing but I want to establish a communication that we are telling to the server facebook.com through the SYN message. The next message the server will send to the client. SYN plus ACK. ACK is nothing but acknowledgement. So the client has sent a SYN message in the first packet. So the server need to acknowledge, right? Okay, I am also accepting the establishment of communication between you and me. To tell that, the server will send synchronize plus acknowledgement packet. Now the client will send acknowledgement back to the server. This is the TCP three-way handshake. So now I established a communication with the server. So here itself we don't get the data. This is just an establishment of a communication after the DNS, after we having an IP address. So once we established a communication through the TCP, the next step is SSL handshake. So SSL handshake is nothing but secure socket layer. Secure socket layer. So nowadays SSL is called as TLS, transport layer security, which is an advancement of the secure socket layer. So this TLS handshake will occur only for HTTPS protocols, URLs. HTTPS is nothing but, for example, here I'm going to www.facebook.com. So here, if we could see, connection is secure and certificate is valid. If we have a certificate and if we see a connection is secure and a lock symbol, this is a HTTPS protocol. And if we don't have that, HTTP, www.example.com, this is not a secure protocol. So this is a HTTP, and which I showed just now, Facebook dot with certificate is a HTTPS. That is the difference between HTTP and HTTPS. HTTP stands for Hypertext Transfer Protocol and HTTPS stands for security here. S stands for security. And this HTTP port number is 80 and HTTPS is 443. So for this HTTP, we don't have this SSL handshake. Only for HTTPS, we will be having an SSL handshake. So as I gave the example of facebook.com here, so the next step after soon after the TCP handshake is SSL. SSL is nothing but here I'm having a client and this is my server. So my client will send a client hello message, a client hello message to the server to establish a secure communication. Because in the TCP, we just established a communication, there is no security in TCP. In SSL, we are establishing a secure communication. So, in this secure communication, the client will send a client hello to the server. In the client hello, it includes client random. Random is nothing but any random number. So 123 A46 or 123 567, any random number the client will send to the server. Client random and the session ID. This SSL session ID and also TLS version. So as I mentioned, TLS is an advancement of secure socket layer. We have a TLS versions of 1.1, 1.2 and 1.3. So the client will send this version which the client is using currently. So the TLS version. And the last one is cipher suits. Cipher suits are nothing but an algorithms which is used to encrypt the message which is sending to the server. Okay. So what all are the things will be exchanged in the client hello? Client random, session ID, TLS version and cipher suits. So now the server will share the server hello. In the server hello, now server will also share the server random and session ID and the TLS version which server is supporting, and it will choose one cipher suit from the list where the client provided here in the first message. It will choose one cipher suit, and along with this the server will add one extra message. This is nothing but one extra thing here, that is certificate. Okay, this is the two message, and the third message is again sent from the client to the server. Here the client again sent a client random which is nothing but pre-master key, which is nothing but a pre-master key. Here it is clear, right? Client random is nothing but one random number the client will choose, that machine will choose. So this client random number in third message is nothing but a pre-master key, and this pre-master key will be encrypted by the public key of server. This public key has got to the client from the certificate which was shared in the previous message by the server. For example, if we go to the facebook.com here, and here I just expanded the certificate. Here we could see a public key column. So once we have a certificate to the client, we will be having the public key. To encrypt the data for more security purpose, this pre-master key will be encrypted with the server public key. Once we have a pre-master key to the server will now decrypt the pre-master key. How the server will decrypt the pre-master key? Because server will be having the private key. The server holds a private key, but the client don't have any sort of public key or private key which holds by the client. The client have only the server certificate. From the server certificate, the server public key will be seen. So with that public key only, it will encrypt the pre-master key. So the decryption of pre-master key the server will do by the server private key. This is the fourth step, and coming to the fifth step. So now client and server, both the parties having the client random, server random, because they exchanged in the previous steps, and also pre-master key. So these three things will go under a cryptographic hashing algorithm method. So one hash will be generated. For example, this client random is 1, 2, 3, 4, 5, and this server random is 5, 6, 7, 8, 9, and this pre-master key is 10, 11, 12, 13, 14. So with this, it will generate one kind of number. Okay, these are nothing but the algorithm which is going under a cryptographic hashing method. So with the help of these keys and this information, the client and server, both the ends, will generate a session keys. Both will generate a session keys. So once the session keys has been generated, the actual application data will flow. The client will send an application data to the server. So server will have a session key to decrypt, and the server will encrypt the data with the session key, so that client also having the keys, session keys with client. So the client will also decrypt the data. This is how the SSL handshake happens. Then only the client can see the information. I can show you here. So here we could see a TCP three-way handshake, SYN plus ACK, and ACK. So this is the URL. Soon after the TCP three-way handshake, we could see a client hello, server hello. And here we could see a certificate exchange. Once the certificate has been exchanged, we could see the application data. Application data is nothing but the actual data is flowing here. Okay, this is about the SSL. And the next topic which we discussed earlier is DHCP. DHCP is nothing but we have a client and we have a server. We have a multiple servers. DHCP stands for Dynamic Host Configuration Protocol, which have a port numbers called 6768. Server will use 67 and client will use 68. So what is the use of DHCP? DHCP is basically used for assigning the IP address. Without the IP address, how can we reach to any servers? First, I should have some recognition. Then only I'll be able to communicate with my name. As I have my name is Bhavna, so I'll be able to communicate with all. So that if you call with my name, I'll be able to respond. Without any IP address, how can we respond? So to get the IP address assigned to my machine, that DHCP will take a responsibility to assign an IP address to my device. So this is client and these are the servers. We have a many DHCP servers. So my client will send a discover message. So discover message to the client. So my client is requesting in discover message, I need an IP address, through the discover message to the servers. So this discover message will send to the other servers also. This discover message is a broadcast message. Broadcast message is nothing but when from the one specific client the same information is sent to all other servers is called broadcast. If it is a unicast, only one to one communication. Okay. For example, you can take a WhatsApp group. WhatsApp group is a broadcast. We can post something in that group so that whoever belongs to that group will be having the information. If it is a one to one, we will be directly pinging the individual person. That is a broadcast and unicast. So the discover message will be a broadcast to all the servers. Now, one server, it is something the first come first serve basis. The server who will respond first, it will be continuing the further communication with the client. Okay, once the discover message is sent, that is, I need an IP address. So the server will respond with an offer message. Offer is nothing but it will share the list of IP address. You can choose an IP address among this list. Now the client will send a request message to the server. Okay, I am choosing this IP address from the list which you provided. So now the client will give an acknowledgement back to the client. Now the server will give the acknowledgement to the server. Okay, you have chosen this IP address. So you need the other information also. Other information is nothing but gateway IP address and the subnet mask. So yeah. Now we have a one more message called. So as DHCP relies on DORA process. DORA is nothing but discover, offer, request, acknowledgement. Other than four messages, we have one more message called negative acknowledgement. Negative acknowledgement is nothing but as I mentioned. So the client will share a request, discover message to all multiple servers, right? So this server has been responded first. So my client will now communicate further with only this server. So what about the other servers where my client has sent a discover message? So all these servers will provide a negative acknowledgement to the client. Okay, you already got an IP address. This all will send a negative acknowledgement to my client. This is something regarding DHCP. So yeah, Vishwa, is it clear for you now? So you missed that class. That is the reason why I just
Okay.
provided this recap for you.
Yes, thank you. Thank you so much.
So now today let us discuss regarding TCP header. Is it clear guys for everyone till now? DHCP, DNS, HTTP, HTTPS, OSI layers and SSL handshake and how exactly the URL work in background. Is it clear for you guys? So that I'll be
Yes,
go
it's
ahead with.
clear.
Okay. And I hope everyone is doing practical labs also, right? By browsing URLs and checking the packet captures.
Yes.
Okay, great. So yeah, let me present my screen again. So yeah, so TCP header. TCP is nothing but transmission control protocol, as everyone know. And this TCP is works at the transport layer of the OSI model. So the complete networking only belongs to this OSI model. It is completely responsible and it only works on the OSI model. In OSI model, we have a seven layers, right? What all are those layers? Application layer, the seventh layer, presentation layer, session layer, transport layer, network layer, data link layer, and physical layer. And the application layer is used only for the human interaction. For example, I'm browsing any sort of applications here. This is readable and this is understandable because of the application layer. The presentation layer, if I'm opening the Wireshark, I'm able to understand, right? This belongs to this source port, destination port. It is only because of the presentation layer which is presenting in a proper format. Session layer. Session layer is responsible for I am browsing facebook.com. So it is responsible for terminating or initiating the connection with the facebook.com. Transport layer. I'm browsing this facebook.com. So this facebook.com requires a port to communicate further. Like here, if we could see, I need a two different ports to communicate, source port and destination port. My source port is 57189, which is a random port, and the destination port is 9000, which is fixed port. Okay, so that will be decided in a transport layer, and the network layer, which I'll be getting an IP address, and the data link layer, which I'll be getting the MAC address. For every device, we will be having a MAC address. So if we could see here, this is my LAN adapter. Physical address is nothing but a MAC address. And the IP address is nothing but this IPv4 address where my device has been assigned to. And this is the subnet mask. And the physical layer is nothing but the medium which is used, the physical things like wires, LAN, where the data will be streamed. This is the TCP, complete OSI model. I just gave a brief so that the new candidates will be able to understand. Ravikant, are you following? And
Yeah, I'm
Murali
following.
Krishna, what about you? Are you able to understand?
Yeah, yeah. I know the OSI layers on modules.
Okay, okay, great. That's great.
Yeah, yeah.
Yeah, yeah.
So, yeah. So, as we know, TCP is a transmission control protocol, which is a heart and brain of OSI layer, which works at the transport layer. And the TCP is a connection oriented and it is a reliable. Why it is called as connection oriented? Because it provides an acknowledgement back to the server. If it is a UDP, UDP will not send an acknowledgement. Okay, I have received this much of data. That acknowledgement will not sent by the UDP, but the TCP will acknowledge. Like I received this much of data, you please send me the data after 5. So this connection orientation is there from the TCP and it is reliable because if I lost some data or else if my data is corrupted, that will be retransmitted again by the TCP because TCP use a checksum which is used to detect the error control. So it will detect the errors and it will control. So yeah, let's start with the TCP header. First, the TCP header. The minimum TCP header is of 20 bytes and maximum it can be up to 60 bytes. Okay. Yeah. So here we have the TCP header includes all this. I request everyone to make a note of it. Okay. Source port address. This is of 16 bits. I hope everyone knows what is 1 byte. 1 byte equal to 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. This 8 bits equal to 1 byte. Okay. So it is of 16 bits. That means it is of 2 bytes. So the source port will be always a random port. If I'm browsing any sort of any websites, so the source port will be a random port. Here we could see 57189. This will be a random port. And the destination port will be a port 80 or 443. Here it we could see a 9000. Let me disable my proxy and let me start the Wireshark packet capture. In the destination port, we will be seeing port 80 or 443 because any website related URL traffic we could see if it is a HTTP 80, or if it is a HTTPS, we could see a port 443. Here, let me open browser. Let me refresh facebook.com, Snapchat. Here I just stopped. Frame contents, facebook.com. So here you are able to see this, right? The destination port is 443. Earlier it was 9000 because of my proxy, that is my proxy listening port. That is the reason why we were able to see the 9000 there. So here we could see, so the source port always it will be a random port, and here the destination port will be a port which we were using. If it is a HTTP, here we will be seeing a 80. If it is a HTTPS, here we will be seeing a 443 because it is a secure. So I just followed the facebook.com stream. Love me a minute, guys. Hello. Yeah, team, I'm back. Thanks. So yeah, where are we? So as I mentioned, the source port will be a random and the destination port will be the URL which we were using here. And here, let me write the destination port is also a 16 bits. Okay. This is also 16 bits. Are you clear, everyone? What is source port and what is destination port? Everyone? No answer?
Yes.
Everyone on mute? Okay.
Yeah, yeah, clear one.
Yeah, thank you. The next one is sequence number.
We can write as 2 bytes and 2 bytes, right? Because you have told uh,
Mhm.
total length would be 2260.
Yes, yes, you can write.
Why to write 16? I'm confused. Let's write as 2 bytes.
Yeah, that is there. But in interview point of view, they might be asking you,
Okay,
or
but
else you can also
first
tell that.
we are okay.
Yeah. So here the sequence number, it is of 32 bits. Okay, the sequence number is nothing but, let me open a Wireshark again. So this is a SIM packet which I'm opening here, and this is the transmission control protocol header, the TCP header. As I mentioned, the source port will be random and the destination port will be 443. The sequence number initially it will be a 0, and the acknowledgement number will also be 0 because it is a first packet where we have been just started a communication. That is the reason why we don't have an acknowledgement back. That is the reason why it will be a 0. Coming to the next packet, we could see the sequence number equal to 0 and the acknowledgement number we are getting to the previous packet. That is the reason why it is 1. Basically, sequence number is nothing but, so I'm just sending first packet, second packet, third packet, and four packet. Four data packets. So if I have any sort of identification, then only I'll be able to sequence it when I receive here. If I receive 3, 1, 4, and 2, in this way, I have to reassemble this back rate. So for that purpose, we have a sequence number so that the receiver end can reassemble the packets. That is the use of sequence number. Acknowledgement number, as everyone know, we are giving an acknowledgement. As I received the first packet, okay, I'll be giving an acknowledgement number as 1. So I received the second packet, I'll be giving the second. So here how this works is basically, so my my sequence number is 1 plus I'm sending the data of 500. Okay. So my acknowledgement number will be 501. Okay. With the sequence number plus the data which I am receiving equal to acknowledgement number. What is the acknowledgement number? For example, if I receive, my sequence number is 10. If I receive 688, what is the acknowledgement number?
698.
Yeah. So this is how we will be providing an acknowledgement back to the sender. This is also 32 bits. Okay. And coming to the next one, header length. This is something a TCP header. This is of actually 4 bits. Nothing to do with this. This is the header length of the TCP header. That's it. And coming to the reserve bits, we will be having a reserve bit. This is only for reserving, and this is of 6 bits. Just for a buffer, we will reserve the 6 bits. And coming to the important thing here, the flags. We will be having a 6 flags. 1, 2, 3, 4, 5, and 6. The first packet is SYN, which is synchronized packet. So when we were establishing a communication, as I showed in the yesterday's class or day before yesterday's class, I don't remember. So if we extend this TCP header, we could see a SYN set to 1 because it is a synchronized message. So when we were sending a synchronized message, the SYN will be set to 1. In this way only we will be able to recognize which packet it is, whether it is a SYN packet, SYNAC packet, or else acknowledgement, only an acknowledgement packet. So it is a SYN packet, we could see SYN set to 1. If it is a SYN plus acknowledgement which is coming from the server end, how we will be identifying? Here we could see SYN set to 1 and also acknowledgement set to 1. If it is only an acknowledgement we are getting, we could see an acknowledgement set to 1. So SYN we have, acknowledgement flag we have, and also we have reset. Reset is nothing but, for example, if you are browsing some URL and suddenly you are entering some details, login details here, you are entering the credentials, but by mistakenly you have closed this, or else some network congestion has happened or some internet connection disconnections you are facing. In that time, the reset flag will be sent to reset the connection. Okay. In that case, we will be seeing a reset flag. Let me check if I have any sort of reset messages here. Yeah, this is reset. So here you are able to see the reset plus act. So let me expand this flags. So here we could see reset set to 1 and acknowledgement set to 1. This is the reset flag. And we have the flag called finish. The same example again. I just browsed the Snapchat and I entered my credentials. I retrieved the data. I have done the task with the Snapchat. And later I just finished. I don't want. So I just want to disconnect the communication. So simply instead of closing this tab or closing or just completely shut down the laptop, I'll be just doing a logout. In that case, we will be seeing a finish. Let me show here. Yeah, this is a FinAct packet finish. So when I expand this here, we could see a finish. So and also we have a push and also urgent flag. Push, urgent. So basically, how many flags we have?
6.
So first one is sin.
And second one is syntax and synact
Second
and
one is not synac. Sin plus
acknowledgement.
act is that is just yeah, we have to tell only sin acknowledgement, push, and also we have reset flag, and also we have urgent. I'll tell about urgent and push, and also we have finish. Did I covered everything here? Yeah, 6. So when the push flag is set to 1, push flag is basically it is rare. So the receiver want the data to be pushed immediately. It is not like an immediately. For example, I got 1 2 3 data bits. Now I'm expecting the fourth data bit. I'm asking the server, please push the fourth bit which is required for me. In that case, the push flag will be set to 1. And coming to the urgent, so I need this data immediately, so then the urgent flag will be set to 1. And we will be having, and one more thing I just missed here, each flag have one bit. So here completely we have 6 bits again. 6 flags, 6 bits. And one more thing, we will be having an urgent pointer in this TCP header. Here we will be having, actually, let me cover here only, because when we have a urgent flag set to 1, this urgent pointer is of 16 bits, which plays a crucial role. Because, yeah, I have to erase something. 1 minute. So one, so urgent flag is set to 1. Urgent pointer, what it will be doing is, so I don't want now the fourth bit here. I received 1 2 3 bit. Now I don't want fourth bit. Now I want 8 9 6 bit. So when I need this data, the urgent pointer is the one which will locate this place, this pointer. It will point out this data. When the urgent flag is set, the urgent pointer will point out the data which is required to me. That is the role of urgent pointer. So here we have a window size. Window size is also of 16 bits. Basically, window size is nothing but, so my client is capable of receiving 1 MB data. So I am asking the server to send me the 1 MB of data. So this is where in a TCP header it will be advertising the capability of the size, the memory. So that is responsible by the Windows size. And the next one we have is checksum. This is also of 16 bits. And the checksum, as I mentioned earlier here, the checksum is where it is an error control detection. It plays an error control detection. So my data has been corrupted. In that case, it will send a retransmission. So it will provide a retransmission of data here. So this much of data is corrupted. I'll be resending it again. That is responsible by the checksum. When the data is corrupted, the checksum will responsible, and it will provide again the accurate data. And this completely of this all bits of 20 bytes. And if you observe here, every bit belongs to 32. Every, I mean, in a column wise, everything sums to 32 bits. So source port is 16, destination port is 16, it is sums to 32 bits. Sequence number is 32, acknowledgement number is 32. And this header length is 4 bits, reserve is 6 bits, which is 10, and this is 6. And this is complete 16 bits, and this window size is 16. This is also again 32 bits. And checksum is 16, and urgent pointer is also 16. Again 16 plus 16, this is also 32. So here everything will be 32, 32, 32, and 32. And here these are the last field options. This will be 40 to 60 bytes, where we will be using for buffer purpose. So in the option fields, this is where we will be having a different types of optional fields. One is MSS and SAG permitted. And the last one is Windows scaling factor. Okay. So MSS is nothing but maximum segment size. So when I'm sending the packets, this should be of only this much MSS. So these capabilities will be exchanged in the option. So my client will be sending to the server. So I'm capable of this much MSS. I'll be able to receive only this much MSS data chunks. So in that case, MSS is nothing but maximum segment size. And the maximum segment size will be, so first you have to know about the MTU. MTU is nothing but this is the maximum transmission unit, where on the physical layer we will be having a wires. So in this wire, the maximum data can be transmitted is 1500 units. This is the maximum transmission unit, MTU. So if we detect the IP header. So now we are talking about the TCP header actually, which is of 20 bytes. And in a similar way, we will be having an IP address. IP header is also of 20 bytes. So if we deduct 20 and 20, we will be having a 1460 as an MSS. So MSS is nothing but a 1460, which is deducted by the MTU from the 1500 maximum transmission unit. We will be deducting IP header and also TCP header. That is an MSS. This will be a interview point of questions. They will be asking what is MSS and why MSS is only 1460. So you have to answer as MTU is 1500. After deducting IP header and also TCP header from the MTU, it sums 1460. So MSS is nothing but in an optional field. Our client and server will advertise the capability of their MSS. I'm capable of taking this much amount of transmission data unit. So coming to the SAC permitted. The SAC permitted is nothing but, for example, I have received 1, 2, 3, 7, 8. And what about 4, 5, and 6? So this data will be identified by the SAC. This is nothing but selective acknowledgement. So when a data is missed by sending by the server or it might be from the client, so in that case the SAC will plays a role and it will provide from 4 to 6. It will not provide 4, 5, 6, 7. It will directly provide 4 to 4 to 6 data is missing. So the SAC will be sent like this: 4 to 6 data is missing to the server. Please reshare me the 4 to 6 data. I don't think so. Here now I have such things where I can show you. Yeah, we don't have here. So here you are able to see the maximum segment size. As I mentioned, 1460 bytes. The 1460 is nothing but how we got this 1460. Can anyone tell me?
Yes.
Yeah, could you please tell me how we got this 1460 bytes here?
Like we are taking 2020 from IP header and TCP header.
From the maximum transmission unit, right? Okay,
Yes.
this is the optional fields which I expanded, which we covered just now, MSS. And the next one, which I'm talking about, this SAC permitted. Here you could see the option called SAC permitted. So when we have a data which is actually missing here, below the SAC permitted, there will be an another column will be added, like 4 to 6 data is missing. So then my server will be able to identify, okay, SAC permitted has been set to 1. So this much of amount of data is missed. I have to reshare that data again. And coming to the last one, which is nothing but window scaling factor. Window scaling factor is nothing but, as I mentioned about the window size, it is server and client will advertise the capabilities of receiving the amount of data. I am able to receive 2 MB of data in one go. In one transition, I'll be able to receive 2 MB of data. Please send me only 2 MB of data. So if I'm able to take this 2 MB of data, again I have more space. Now I can increase the capability. So how I'll be telling the server to increase my capability. With the window scaling factor, I'll be telling server to please send me now the 4 MB of data. So when we have to expand the limit, the window scaling factor will be helping us. So the window scaling factor will be the maximum 2 power 16. So 2 into 2 into 2 into you have to do. That will be 65535, I guess. And
536.
okay, 536. Thank you. So let me show you here. Yeah. So if you could see, here we could see the window size as 1026. So client has been shared, this is my window size, please share me this much amount of data. So later, this is telling the window size scaling factor as 2 power 250, sorry, just 256. So 256 again you have to do, it comes under somewhere in the 2 power. Okay. So here when I am doing this 1026 into 256, this is of my calculated window size 262656. I'm capable of now receiving 2622656. Okay. So we have to multiply the window size with the window scaling factor 256. That will give the correct window size. So now I am able to receive that much amount of data. This is all about the TCP header. So I want everyone to just recap everything again on the TCP header.